Welcome to another short video from the designers here at BitWise Laboratories. These videos are intended to give you a quick introduction to our instruments to help you understand what they can do, as well as to see them live in action. This video introduces our new Parallel Error Location Analyzer, the PELA. Analyzers, by their nature, are more complex, so this video is a little bit longer than others, just to make sure you get a good introduction to the power of error location analysis. The PELA is a two-channel bit error detector that can synchronize and find bit errors in NRZ data streams at speeds up to 32 gigabits per second per channel. The PELA is enhanced with an exceptional feature to not only count bit errors, but to keep track of the exact bit location, the bit address, if you will, of where errors are. With this information, it can process these bit locations into more analysis of your bit error rate data. These analyses give you insight into what may correlate to your errors, helping you to find root causes. In addition, exact bit error locations can be organized into symbols, and symbols organized into blocks, and blocks can be interleaved, allowing you to see symbol error statistics on block boundaries. This type of analysis is key to understanding correction strengths needed by forward error correctors to achieve error-free performance on some of the channels used today. There are many techniques for studying error location, which we'll get to later. For now, just imagine how much more diagnostic it can be to know if all your errors came in, say, groups of 3 separated by some perfect interval, and how much more diagnostic that would be over just knowing the count of how many errors happened. To get started, let's take a look around the block diagram of the error location analyzer. The bottom left corner here shows the two input channels, which are differentially received, coming into threshold detectors such that we can program a variable threshold of where to slice this each NRZ stream, being put into sample high-performance silicon germanium flip-flops where we can also adjust when to sample them, a variable delay element. This is all tied to an input clock that you can provide. This clock can either be full rate or half rate. That's selectable. And then that goes into our error detector block here, which first synchronizes to the streams and then studies or counts or logs error locations in the detected data. These two streams can be thought of as one stream, as if they were bit interleaved, or as two separate streams. We could have different types of data present on different lanes, as long as they're all clocking at the same rate. The error detector's results are sent to a computer for processing, and the error locations, a log stream of information, can both be recorded to an internal solid-state drive and or displayed in real time up on the graphs of the analyzer, allowing you to see the details of your error statistics. The processor and solid-state drive inside the PELA is running Linux and hosts both user and remote control interfaces. Like all BitWise instruments, the user interface is done using a web server, allowing multiple users to connect to the decombiner using popular web browsers. The remote interface uses a TCP/IP socket to implement familiar Skippy-like commands using simple ASCII text. While it's possible to connect a monitor, keyboard, and mouse directly to the PELA and access the user interface using the browser on the internal desktop, most customers find it more convenient to access the PELA through the Ethernet network. Again, looking at the front panel of the instrument, here we can see the two channels of input data as well as the input clock. The clock can be full rate or half rate. The signals for input can be differential. If you don't use one of the legs, you can terminate it. We also provide input and output auxiliary signals. These are future expansion to be able to support programmable triggers or flags that might help new formats for studying error statistics or gaining synchronization in data streams. On the back of the unit, you can see where we have USB and Ethernet connections, as well as a 12-volt power connection and the on-off switch. In addition is the ID button. This is used to be able to send a ping back to our servers when you want to help identify the local IP address on your local area network. To get started now using the PELA, I'll bring a browser on board. Again, all our instruments are driven by browsers for the user interface. In today's setup, I'm actually using a few of our instruments together. The arrow location analyzer here on the bottom in this little stack. I'm generating signals. I happen to be using our PAM4 combiner and creating a PAM4 signal using our live PAM4 decombiner to strip them apart into two NRZ streams. And then those two NRZ streams are what I'm putting into this analyzer. So we'll get a chance to put patterns in and study them, as well as play with thresholds and cause bit errors and study them in the result. When I bring up a browser, I'm always careful to point out the address that the browser is looking at. It's a familiar website address, if you will. Here I'm using a named address. This is served by my local area Microsoft network setup. If I didn't know that address, I could go to the hard IP address, for example, on the device. Let me see if I can find one here handy. Down below here I see an IP address for this device here. If I was to copy and paste that into, say, a new window and hit Control-V and go to this hard IP address, I can go to that same user interface now through another window, another browser. This is available, so that allows you to have multiple users accessing the same device on different browsers, even on different computers, even in different countries. So let's go ahead and go back to our PELA and just take a quick look around the user interface. Let's start by going over here to my BERT button. This is sort of the most basic function in the analyzer. The analyzer's user interface is broken into a few sort of major areas. Down below here is a control and status area. We'll use this in a minute and go through some of the setups for signals and different analysis modes down here. Over here on the right is a navigational collection of tabs, if you will, where you can pre-assign some of the tools onto different tabs, making it easy to jump back and forth to collections that you like. And up above here, in many of our analyzers, we turn this view off, this toolbar, for example, the show application toolbar, I can turn that on or off. But there are so many different collection tools that I want to show you today. I'm going ahead and leave it open, and we can drag some of these out to take a look. For example, right now I'm looking at the bit error rate detector view. I might also be interested in a strip chart for bit error rate. I might not like them stacked left to right, so I might put it underneath. And I can drag that open and get a chance to see a small strip chart next to a tabular view in this case. Before I get into making bit error rate measurements, maybe we'll first talk about connecting signals. Down here on the status bar, for example, my data rate icon, if I click on that, here I can set the input clock to be full rate or half rate and select a threshold margin if I want on that. It will also automatically search and find the best sampling point for your clock. Link mode is interesting because, again, I have two lanes of data coming in, channel 0 and channel 1. I can tell the analyzer I only want to look at channel 0 or only look at channel 1, in which case I have one lane bit array testers, like you know from the industry out there. But when I use two, I can think of them in one of two ways. One is unlinked. That is that I'll run both lanes simultaneously, but they don't really have to do with each other. So the data lane on one can be different than the data on another, and I can run bit rate tests and make that analysis separately. But there is a special mode that's interleaved where the odd bits might come from one lane and the even from the other, and that makes up a contiguous full rate stream. This is excellent for doing tests in streams that will eventually be muxed, for example, or demuxed. If I go on, once I set, I'm going to use my test here in unlinked mode. I can choose to show the results. For example, if I turn on all channels here, I'll just see separate lanes of data. But if I select to look at both, I'll also get a combination. It'll sum them or make other manipulations when it makes sense to think of them as a combined lane. Each of the channels can be set up. For example, I can set the detector pattern to different pseudo-randoms or ones or zeros or user-defined patterns. I can invert them or not. A favorite setting for me here is the auto pattern, because it'll search through and find which pattern you're using. You can set it to use auto resynchronization, which is also a favorite of mine. Auto resynchronization will look at a contiguous number of words that are coming through. These words are 128 bits each. And if it sees 10 words in a row that have errors in them, it'll think that it has lost sync, and it'll go about finding sync. If that sync is in auto pattern mode, it'll first try the pattern it was in last, and then it'll go about also searching patterns, and then also searching inversions of patterns. And so it'll, in a blink of an eye, it'll find the data that you're using. You can also adjust the sampling delay and sampling threshold that you want that high-performance flip-flop to sample. The nice feature here that I can press the auto set button and it'll search through a pattern and actually find the best sample point and sample time for my bit decisions. I have that setting for both channels independently. If I was in linked mode, there's another button down here that will show me sort of the aggregate sync. Not only will it sync on one channel and then sync on the other channel, but it will also bit interleave the two channels and see that they are in sync. Now this brings up an interesting point. If you have cables of different length and you were counting on these being exactly bit interleaved, that might fall apart. You might not be able to gain sync in an interleaved way. For that reason, we've included a small plus or minus 64-bit barrel shifting feature in the input of the PELA error analyzer. So it will shift through and find the bit position where sync is established. You can, it'll display how many shifts it made to get sync. You can lock that down if you want to force it for future tests, or you can just allow it always to search through. You have access to user patterns. You have large memories for both the error detectors that you can use for synchronizing. One of my favorite methods, though, isn't to predefine a user pattern. It's to use a grab-and-go method, where you simply tell the error detector how many bits are in your user pattern, and it will grab that number of bits, and then it'll check it against future grabs of that. And when it gets error-free grabs of the number of bits that you told it, it will use that information then for future synchronization. It'll just go continue looping that stream for future bit error rate testing. Now I'm getting two green lights here which says I already have synchronization, but that's not always the case. One of the handy things that we've added to the PELA analyzer is the ability to actually draw at least medium resolution quality eye diagrams on the two streams themselves. And here, for example, if I run a single capture, I will run a new incoming stream. I have these icons here that show where my decision points are. I can move them into bad areas. For example, you see the sync I lost because I went into the bad area of the eye. If I go back into the good area, I'll get sync. So the eye diagramming feature has flexible cursors, and I can measure things. Again, if I was looking for high performance eye diagrams, I'd be using a high-end sampling oscilloscope or something else. But this is very nice to be able to give confidence that you have open eyes where you can successfully make bit error rate tests. I'm confident that I'm in the middle of my eyes. I'll go back to my BERT window here and, for example, press the run, and it'll start analyzing errors. And this is a little boring. I'm transmitting bits into both channels. I'm not getting any errors, and that means I'm not getting much of a bit error rate. It happens to be that I'm transmitting from our pattern generator. I'm going to jump over to our pattern generator view for a minute. We have a little error injector here, and I can go in there and cause single errors a few times, and then go back to my error analyzer, and I can see where I get bit error rate measured and a certain number of errors injected into my stream. It's interesting that my error injector was set to inject 64-bit errors on one lane and single-bit errors on the other, and you can see I pushed it 4 times, and that's the detail of the error measurement I can get from counting. Later on, we'll see using those same kind of error injectors, but being able to understand the burst length probability, for example, of different sizes of errors. So let me go ahead and stop that analysis, and we'll move on. Error location analysis, or ELA, is, as I mentioned before, one of the key differentiators of the parallel error location analyzer that we offer. This view shows you a similar kind of bit error rate testing view, as well as some of the console statistics for recording or keeping track of the error location information. For example, if I press the run button here, I'll see a similar error count going on. I'm getting no errors, I'm seeing bits. It's also keeping track of symbol error rate and bit error rate given a particular symbol size that I set up in my basic error location analysis view. This is actually a completely separate bit error analyzer, separate than the error counter that we would see in the BERT view. So in the ELA view, this is done by interpreting error locations. Error locations is a stream of data. That data can be sent to files. For example, I can record them. We gladly publish the format of those files, so you can actually write analysis techniques of your own to study some special interleave or some special error statistic that you might be after, or you might work with us to help write a small analyzer for you as well. As you can see in this case, I'm getting very few errors coming through. My transfer rate at 46 bytes per second. The error location stream is formatted to record error locations, and because I have no errors, I just get a small amount of data going through. Again, if I go over to my pattern generator, for example, and perhaps if I cause a bunch of errors here, I can go back to my PELA and see that this surged upward while it recorded those data for future analysis. The recorded error data is sent to the internal solid-state drive. For example, if I stop this analysis, I have recorded a small error data set, and that's actually in a share location. We support open shares for this purpose, so I can actually, again, just go to a browser and paste that in as a new share, and here I can see, for example, under Error Location Analyzer, the test that I just ran, and I can use this data, offload, I can drag it out or move it off this machine to other machines so that I can perform any kind of special analysis that I want to do. Let's go back to our PELA analyzer and take a look at some of these error location analyzers that we have built into our analyzer. Perhaps the first one to look at is our burst length histogram. The burst length histogram plots the number of times you've had errors of different lengths in bits. So for example, if I go to run this analysis, again at the moment I have no errors, but if I go over my pattern generator and maybe I'll turn on, instead of single errors on our pattern generator, I'm going to set it to repeat a known error rate. Then if I go to my error analyzer, I see this growing bar here. Remember I mentioned that this particular error type was 64 bits, and I'm seeing that all the errors I'm getting are 64 bits in length. Let's demonstrate that a slightly different way. If I was to go over to my eye diagram, for example, and move maybe my decision threshold up here somewhere where I should get a high bit error rate, then I could go back to my analysis of burst lengths. Let's see, where was I? This one. And press my run button. And now I see that I'm getting errors here and here. These are the errors of my injector, and these are errors being introduced by having the threshold slightly too close. I can use my cursors. For example, I can take off my overlays, so I can move this cursor a little bit. These are all small 1-bit errors. I've required that the errors be separated by 2 bits to have bursts. So all of these errors are being interpreted as single-bit errors, which is what you'd expect if you were bumping up against one edge of the waveform in a signal and getting bit errors from that. Notice it is possible that you'd have one of these random errors occur during the time in which your 64-bit error was happening, and that would give us some small occurrence of errors on either side of that. And that's again some of the detail that we can pick off by looking at error location analysis. Let's continue with this example a little bit. I'm going to go back to my pattern generator and turn off that repetitive error so that I'm left with only these errors that are happening because I've moved my decision point. If I go to run and burst length, now I'm back with this small number of errors here. Again, I can go to my bit error rate view and press run, and I'll see that I'm getting errors on that channel. That's the one I moved. And in my strip chart, I'll start to see points plotted. I've set an interval for 5 seconds. I might choose to do that quicker for this analysis, but here I can see my measurements. And it's measuring both the combined and channel 0. That's why I'm seeing the red dots here. Another way to interpret error statistics, error locations, is what we call modulo analysis. In a modulo histogram, we will continue in time, going from left to right with every bit position until we hit some modulo number that you've given us, and then we'll start again. We'll rewind, and this will show us a correlation of error positions to your modulo number. In this case, I set the modulo size to 128 bits, for example, and no real reason yet here. The other setting that I have to be careful is that all our error location analyses can be done in either individual channel mode or as a combined channel mode. So remember, we've got the errors going on only channel 0, so I'm going to do analysis on only that channel. So for this modulo analysis, I'd like to correlate my errors to the number 129. It's not an intuitive number, but it's a number to just start doing analysis on. If I set my correlation to 129 and press my run button here, I see that my errors, if I look down below here in the 129 locations, there's really no strict correlation. It says every spot modulo 129 bits is about the same probability. Nothing is outstanding. However, this is where we start thinking about our system. For example, here we're transmitting bits that repeat every 127 bits, a PRBS 7. If I was to change this to 127 bits, for example, and go to do an analysis here and press my run button, all of a sudden I see a great correlation to the 127-bit number. That is what we'd expect to see, because this error that we've injected is truly a pattern-sensitive error. It would repeat on the pattern boundary. In fact, if I look at my eye diagram and see where I'm causing errors, I would tend to see, first off, it really only on falling edges, and then on a repetition rate, perhaps the one that's caused by the longest run of ones or zeros would tend to be my most offending error or bit transition, and that would cause my bit error to be seen in this graph. Correlations can be done to lots of different magic numbers, and we all know magic numbers in our system, whether it's a 32-bit bus or a block size or something that should not have errors that depend on them, all of a sudden starts to cause errors that depend on them. Then you start to know, well, maybe I have a weak driver or something in my system is causing errors to propagate on those lanes more often than others. How might you find those magical numbers? Well, we use another one of our analysis techniques, the error-free histogram. This histogram plots the interval that occurs between two errors. So if I have error-free intervals, they are plotted in a histogram. Error-free interval, a repetitive error-free interval would say that you don't have a random error, that you have errors that are systematic. And it's those systematic errors, again, that we're trying to find. If I press my run button here on the data that we're using and let this run for a minute, sure enough, I see some repetitive intervals that occur more often than others. I can stop that analysis. I might use my cursors here and might go ahead and find one of those locations and see exactly what error-free interval that I might want to use for doing my analysis. I might have lots and lots of data here if I continue to run. Sometimes error-free intervals can be much longer and show multiple or beating frequencies against errors. That, again, you can use this to spot and work on the math to try to find exactly what error-free interval might be correlating to your error. Another kind of error analysis that is very popular right now has to do with studying the strength, the t-strength of error correctors. So let's go ahead and take a look at this one. For a strip chart of t-strengths, we need to understand what kinds of symbols, symbol sizes and block sizes we might be using, and whether or not they're combined between two channels or a single channel. So we can select the parameters to be able to set that up for the given kind of analysis or simulation we're trying to run. Then I can run my data through here, and the analyzer will show me over every interval of time what correction strength I would have needed to get error-free performance in that interval. Now, unfortunately, the error that I'm causing right now is a little simple. Maybe if I go over to my pattern generator and to the error injector and cause a few of those, single inject, and I go back to my error analyzer, you'll see that there were a few occasions where it needed more error correction strength to pick off those errors that happened in the stream. I've shown you the various error location analysis features. I also wanted to have a chance to show you an analysis we perform on the actual data itself. There are times when customers or users want to understand the statistics of run lengths of their pattern and a wander that might occur in their pattern. And so we developed some small applications here that will use our user patterns grabbing capability and do studying of the numbers of ones and spacings of ones and zeros in it directly. Let me first show you the grabbing capability. It's what's underlying the analysis I'm going to show in a minute. In here I can set up maybe some symbol sizes, a number of patterns, and execute a grab. So I would grab some data. I can choose my format, maybe in hex and 32-bit, actually maybe binary, that's often helpful, and press OK, and that will grab a data file and it will create it here in my user interface so that I can then access that file. To access the file, I would press download, and I would find that file maybe right here and select it and hit OK, and then that file will occur down below here. It's a CSV file, something we're familiar with, and again I can look at my data in gross detail and get a capture of the full bit rate through my lanes right here. The channel I grabbed here, I had selected as channel 0. You can do individual channels or a dual channel capture of that data as well. By using the underlying data capture capability, we can run it again and again and collect statistics about your user data pattern. This isn't error location data, this has to do with your actual user patterns. We can show it in a variety of different ways. For example, here we'll just count the number of zeros and ones and keep track of mark density. Down here, this is a histogram, if you will, of data wander. In data wander, we allow you to give us a number of bits, sort of the integration period, that will keep track of the variations of numbers of ones and numbers of zeros, so that we can see how much wander you might have to track, say for AC coupling a signal on your system. Over here in this histogram, we would show a histogram of the run lengths that are present in your data. So for example, if I came up here and I press my run button on this data, this is capturing portions of my incoming data stream. Remember, my data stream is PRBS7 at this moment on channel 0. And this shows how many maximum runs I'm seeing. For example, this is 7. I'm getting a few 8s, and that's because I have an error injection going on, and sometimes that 7 can be next to 1 and I get an 8. Far less probable. And over here I can see that I'm very close to 50-50 in my number of ones and zeros, and because it's such a short pattern, I'm not getting wander on that stream. Again, this is my stream of data coming through. For example, If I want, I can stop that, make cursor measurements, again, like I can on all my graphs, and study them in detail. I also, again, most all the graphs have the ability to download directly to CSV files. So, for example, I can look at my run length data right here and move it into other tools if I want to do some other kinds of analysis. Well, this has certainly been a whirlwind tour of our parallel error location analyzer. You've seen how to connect signals and optimize. We can look at the eye diagrams and set our sample point. You've seen how to do simple bit rate measurements and look at strip charts of error rates. We've seen how to dive in detail into error location analysis and look at the various different techniques, including burst length histograms, error-free interval histograms, correlation analysis through modulo histograms, as well as error correction strengths. And finally, at the end, we also looked in detail at some other tools focused on looking at the actual data pattern you're using to understand run lengths and any kind of wander that might be happening. We really want to thank you for watching this video on our PELA error location analyzer. Again, we're sorry it was a bit long, but we hope we did a good job in introducing the instrument as well as showing you the power of error location analysis. We know there's going to be a learning curve for using our instruments, so feel free to contact us with any questions.